So I'm going to be talking about entropy and Gibbs free energy and kind of like how they work with each other and how they relate to each other. So entropy, basically, I'm just going to give the web definition and then actually explain what you can kind of like the physics behind it. So entropy is basically just a thermodynamic property, often defined as disorder in the system, but disorder is a very vague term, right? So is it a disorder of the molecules being spread out, or is it a disorder of the energy distribution in the system? So if I were to draw this out, I'm gonna do like a matrix of energy basically, and it's gonna go up to 3 as max because I can't count to 4, so it makes it easy. So everything's gonna start out as 1 energy, basically, and this, let's pretend this is like a room of molecules, and we're just gonna add a little bit of energy into the system, right? So what entropy essentially is, once this energy is added to the system, these energy levels, let's say they change to 3, and because high energy likes to move to low energy and like give it in that direction, what ends up going to be happening, assuming that entropy is being nice, is it's going to evenly change these to 3. But the problem is with entropy is now there's 2 directions this can go. This is 1 and this is 1, and ideally it only wants to flow in 1 direction. So think of like electrons carrying energy. They flow through a wire, that's how it carries energy, and they don't go backwards, right? But the problem is with heat distributions, they can go backwards. So the way entropy is increasing in system in this case is, let's say for this becomes a 1 and it goes back to a 3, but these transfer in this direction. So what this creates is disorder. So essentially, instead of this entire left side, this column being all 3s, the energy moves smoothly in, it accidentally got distributed backwards. And what this causes is the entropy in order to reorder the system is now higher. So and think of entropy as the required energy to bring a disordered system into an ordered system. And that's why it's a loss, because all systems want to even out their energy, right? In order to even out that energy, it requires creating entropy. So the more disordered the starting position is, the higher the entropy, or the more entropy will be produced. Hope that makes sense. So next, I'll talk about isentropic processes and kind of what that looks like in this case. So in isentropic process, basically, obviously what it says is entropy is constant between states A and B. So think of like a thermo, like cycles, it's like a vertical on a TS diagram. So the entropy 2 states are the same. And this is the basis for comparing ideal systems to real systems, is we want to look at what's the minimal amount of entropy we can, I guess in this case, the 0 amount of entropy we can produce by accident, think of the most output and relate that to what we actually have as a system, which will always have entropy production. So this is also useful if you have like an isentropic process, and the equation is obviously the ideal gas equation with K, which is just Cp over Cv, I think. And this allows you to simplify gas systems in any gas equation if entropy is constant. So if we were to look at this little box again and what this would change, and let's just say we have a continuous flow of energy. Basically, let's just say this is continuously adding energy and it only goes up to 3 because I can't count. Basically, the energy is always going to move in 1 direction, just like electrons. Oh, I guess it moves 3. So just imagine like it goes like flows that direction, right? So now this is an ordered system. All the energy distributions are even, and nothing changed, right? There's no need to disorder or to order the disordered system. It's an ordered system already. That's basically what the isentropic process means, is that the energy distribution as it flows into an object or gives out energy is completely linear in a straight line. It doesn't go backwards, goes in random directions. It's just an ordered distribution. So if we look at like Rankine cycle, right? I'm gonna draw this here. So what does it look like if it was like not isentropic? So we're just gonna look at the turbine part because it makes it a little easier. So let's say this is point A, this is point B, and this is your constant. I guess I should ignore the fact that there's no zero. But so this is the TS diagram, and from here to here is an isentropic process. So if it wasn't isentropic, let's say it starts out and we're doing a non-isotropic process, and the entropy doesn't change as it goes down. But suddenly, like say this here, and with that previous demonstration, some of the particles give energy in the wrong direction. This will create a deviation slightly. And let's say that happens again, let's say that happens again, this happens again, and it goes like here. So this will create what we normally see is a non-ideal, or non-isotropic like state phase change in like a Rankine cycle, for example. And that's just kind of like what it'll look like visually, which is those incremental like bad distributions of heat when energy is changing in the system creates this not isotropic phase change. So next up is Gibbs for energy. Again, just gonna give a web definition about it. It's basically a thermodynamic property which essentially tells you the potential of a system and whether or not this like a reaction is going to be spontaneous or not, and I'll explain that. So what does Gibbs for energy and entropy have to do with each other? So this basic equation is just basically a thermodynamic formulation, and I'm sure I'll put everything out. So when Gibbs for energy is positive, this basically means the system has potential to give out more energy, right? So what does this mean like mathematically? So if you have a certain temperature, so normally when this is explained, temperature and pressure are constant. So the internal energy cannot change. The temperature cannot change, the pressure cannot change, but the volume can change. So what this means is when Gibbs for energy is positive, is there's more volume change that can happen to give out more work, which will result in an increase in entropy. That's just what will happen when you increase the volume. Similar to the previous explanation with more movement of the molecules, like more room to move. That's like also kind of creates this order in its own, like, right? So as the volume increases, you also get more work when you're expanding, like expansion. But this will result in an increase in entropy. Eventually, those will meet up. Gibbs free energy will start reducing, and you'll basically be using up that free energy that you previously had with the, I guess, the previous volume. Oh, wait, yeah. So I forgot to say, Gibbs free energy can never be zero. So the reason for this, if you think about it like thermodynamically, Gibbs free energy is basically just the energy of something. If it's zero, like it can't just use all, like a particle cannot have zero energy. That just makes no sense. Like that just cannot happen. So Gibbs free energy is basically just a non-zero value. So what else can this tell you? So another thing this can tell you is when you take the derivative of the previous and you just look at the changes in the system, this will also tell you whether or not a reaction can become spontaneous or not. So the spontaneity is not just like a blade turn. Basically what happens is in the system, if you have enough entropy, which means the particles have a higher energy distribution, they're more disordered, that basically means they move a lot faster. And reactions require contact time and like contact angles in order to happen. So when a system is more disordered, the molecules have to move a lot more in order to create a more ordered system, which creates more chances for a reaction to happen. And this is why when you have a negative change in Gibbs for energy, or like positive change in Gibbs for energy, the reaction becomes more spontaneous. Any questions?
Your explanation of entropy, like, it's pretty interesting.
Yeah, I like this explanation of it because it makes a lot more sense because it has like physics behind it. So instead of it just being a blank term, there's like some form of physics about actually how it works. Yeah. A buddy of mine like explained this to me a couple of years ago. So this is kind of how I've always been thinking about entropy.
So just one question for you, please.
Yeah.
Does that mean like isentropic processes are the best process? So an isentropic compression and an isothermal compression, which of these two compressions would require the minimum amount of energy?
Isothermal?
Yeah.
It should be isothermal.
Isothermal.
Because temperature has the biggest effect on state property changes because that's the basis for energy. So if that makes sense, because like everything's a function of each other, like in thermo, but temperature has the biggest impact on all the other properties because it's essentially just carried energy.
Yeah, that's correct.